All right, so without further ado, I am delighted to introduce our first presenter. Please join me in welcoming Joel Ambriz from UW-Parkside, whose presentation is titled, "Which crystal phase of silicon is stable in 10 nanometer thick membranes?" Take it away, Joel.
All right, are you guys able to see me? Well,
looks great, Joel.
All right, thank you, Tony. All right, well, hello everyone. My name is Joel Ambriz Ponce. Y'all can call me Joel, and I'm from the University of Wisconsin-Parkside. Today, I'll be trying to answer a question that's related to my recent investigations, and that is which crystal phase of silicon is stable in 10 nanometer thick membranes. Next. So overall in today's presentation, alongside that question, I hope to answer a couple other questions that are related. And those questions are, why are these 10 nanometer thick silicon membranes important? What method do we use to model the behavior of the membranes in question? What process do we use to create a stable model for the structure at hand? What behaviors are we trying to extract properties for? What properties does our model suggest? And after that, we'll end it and go on with the questions. Next. So first of all, why do we even care? Well, silicon is one of the most widely used materials in the modern age, with many applications in computers and microelectronics. Also, electronics have been getting consistently smaller in size over the years. So what we'd like to know is how silicon behaves at these smaller scales to help with future applications. Next. So in my investigation specifically, how we investigated it was we used a theory called density functional theory, which is a theory that uses the electrical density of the structure along with some quantum mechanics to obtain the properties of the system. As to why we use this theory, well, creating the actual structures requires tools and technology that not everyone has, and here at Parkside, we didn't really have the technology and tools. Also, particles at the size of electrons are subject to the laws of quantum mechanics, so that makes them perfect candidates for the density functional theory. And without density functional theory, we would have to take into account the 3 spatial coordinates of every particle to make calculations, which would take a lot of time and computational power. Density functional theory simplifies this to just 3 spatial coordinates, which saved us all those resources. Next. For my specific investigation, how we use density functional theory was in a program called Quantum Espresso, which was already coded with density functional theory. What we had to do was input a couple different things. For example, the coordinates for atomic positions, simulation self-parameters to fit our atoms in, and other parameters specific to our atoms, such as the type of atom, in our case, silicon, and some program thresholds. I should also mention that the Quantum Espresso program, the cells specifically, exhibited properties which were periodic boundary conditions. This meant that the atoms near the edges of each phase interacted with the atoms near the opposite phase in the cell. And this would allow us to simulate an immense amount of atom interactions, which would mirror how real-life materials work. Next. Now, in this slide, I'll show how we created the stable structure, which answers the first question the first slide in the presentation. And this was done after we input our parameters into the density functional theory code. It was done in a couple different steps. First, we would start with a model for a bulk material, after which we would add a region of space to the cell in one direction to get rid of the periodic boundary condition in that specific direction and obtain membrane behavior. After that, we would relax the structure to obtain the lowest energy state of that structure, then calculate the atomic vibrational frequencies, for which it would give us an idea of how stable the structure with imaginary frequencies, implying that the structure was unstable. If the structure wasn't stable, we would move on to the next step. If not, we would stop there. But if we did move on to the next step, what we would then do was move the atoms, relax the structure, and calculate the frequencies again. We would repeat this step until we were satisfied with the stability of our structure. Next. After obtaining our structure, we would then run calculations. But in order to understand the calculations or the data for the calculations I'll show you next, you would have to understand the background for what happens in silicon bulk material. Usually for bulk quantities of silicon under ambient pressure and condition, there occurs a phase transition from diamond phase to beta 10 phase when pressure is applied. And what we got the properties for was basically in order to compare how the silicon membranes or the properties for the silicon membranes compared to that of the silicon bulk. Next. After running the calculations, we ran calculations for both the membrane model, well, at 8 atoms thick and for bulk. And since we don't have much time, I'm just gonna summarize some of the properties that popped up. Some of them one that really popped up was the transition pressure, which for the membranes was negative and for the bulk was positive. And this seemed to suggest that there was a reverse transition in the membranes comparing that to bulk. Another interesting property was that of the bulk modulus, which is basically a measure of the elasticity of a material. For the membrane in the diamond phase, it was way lower than that of the bulk diamond phase. Also, for the beta 10, it was the beta 10 membrane phase, it was opposite, because for the beta 10 membrane phase, it was way higher than that we got from the bulk beta 10 phase. And these properties, or this data set, seem to show that either the membranes of this thickness seem to have significantly different properties than that of bulk, or that our model needed more stabilizing. Next. And that'll be it, since this is a short presentation. But overall, in today's presentation, I hope you all got that technology which uses silicon is getting smaller in scale. So knowing how the scale affects the silicon material properties will help with future applications. Also, that density functional theory is a good way to model these structures to obtain their properties, and that there's a simple process to obtain a stable structure model once we use this theory. Also, in bulk material quantities of silicon, the pressure induces a phase transition from diamond phase to beta 10 phase, and that in our membrane model, these properties vary significant from that of bulk material. That'll be it for today. Thank you for listening to me.
Great, thanks, Joel. Does anyone have any questions for Joel? Feel free to turn your mic on.
I had a question. Your boundary, so it looked like you had boundary conditions along one dimension, but not the other when you allowed them to relax. Is that correct?
Yes.
Okay. Okay. So, okay. I was just trying to imagine how that would work, relaxing with a periodic boundary condition, but I guess, okay.
Yeah, that would make it so that in one direction, the atoms interacted, or in two directions, the two planar directions, they would interact, but in the, in the other direction, they would not. So that would simulate a thin structure.
Okay. Okay.
Yeah, thank you for your question.
And was there another question out there?
I do have a quick question. Could you explain the negative pressure and the reverse transition that you talked about in that last summary slide?
Well, this was done by taking the equation of state of the diamond phase and beta 10 phase for the both data sets for the membrane and the bulk. And in bulk, the transition goes from from diamond phase to beta 10. And that usually gives us a positive transition pressure. For the membrane, the data we got gave us an opposite transition pressure, which I'm assuming suggests that there was a reverse transition than that that happens in bulk.
Okay, I guess maybe a question wasn't super clear. Does a positive pressure mean compressive and a negative pressure is in tension? Is that what we mean by positive and negative pressure?
Yeah, it was a bit weird.
Maybe you could talk about the energies of the two structures.
The energies of the two structures. Well, if I remember correctly, the energies we obtained for diamond were low, or in the membrane at least, the membrane structure, they were lower than that we found in bulk. In fact, they were way lower than that of the beta 10 phase in the membrane model. And that suggests that, or usually structures go tend to like to go to the lowest energy structure, which in our case, that meant that it would go from the beta tin to the diamond, since the diamond was a lower energy structure.
Got it. Thanks. Yep.
Thank you for your question.
All right, thanks everyone. And thank you, Joel.